Okay. So we talked about the dielectric constant. I defined it. Specifically, I defined it as the ratio of the dielectric constant of whatever material you put inside the capacitor plate. By the way, let me back up a step in a second. It's not realistic the way I just described it. What actually happens is you decide, or the manufacturer decides that they want to make some capacitors that are able to store a certain amount of charge. And so then what they do is they say, okay, we'll construct it out of plates that are this big with these dimensions made out of this material, this far apart from each other. And then in addition, we will design it so that every capacitor we build will have this much Teflon or this much paper or this much petroleum jelly or whatever they decide to put in between the plates, whatever dielectric they decide to put in the plates. And so they choose the dielectric that they want based on how much charge they want to store, and so they look at in some sort of a reference book what the dielectric constant is of various materials, pick one, build a capacitor with those. So the way I'm describing it, which is you take a vacuum capacitor, in other words, a vacuum where there's a capacitor where there's vacuum between the plates, and then you measure the capacitance, and then you stick some dielectric material into it and look at the change. That's not realistic. That's educational. That's a way to think about it, but that's not how they actually build capacitors in industry. With all that understood, okay, so a capacitor with a dielectric compared to an otherwise identical capacitor without the dielectric, they're going to have different capacitances. Okay? So let's take a look at that. I did a few lectures ago a calculation where I came up with a theoretical expression for the capacitance of a parallel plate capacitor, one constructed from rectangular plates. And I showed back then that the expression that gives you C is the area of one of the plates divided by the distance between the two plates, and then that is multiplied by the permittivity of vacuum. But now, to give you a little more context and understanding, the only reason I multiplied it by epsilon naught was because I made the unspoken assumption that the stuff between the plates was nothing. I mean, there was only vacuum between these two plates. Okay, but that's almost never the case. And so when it isn't the case, if we deliberately insert some dielectric or build the capacitor with a dielectric, then we can't use this value because that's only for vacuum. We have to use the permittivity. We have to use the permittivity of whatever new material we decide to use. Okay. So I need to alter this. So it's vacuum. Now here's a new thing, but with a dielectric between the plates, a small but crucial change to the expression. So let me call this C sub VAC for the capacitance of a vacuum capacitor. And then here I'll just use C for the capacitance of a real capacitor. This is going to be, it's still the same area plate, still the same distance between the plates, but now we'll use just epsilon without subscript 0, indicating that we're looking at the permittivity of something that isn't vacuum, whatever our dielectric is. Okay? And now the question I want to ask is how are these two expressions related? How does the capacitance differ with and without the presence of this dielectric? How do we calculate that, I mean? It turns out to be surprisingly simple, and maybe you've already seen it. Because epsilon, actually I just moved away from it, so here it is. epsilon and epsilon naught are related to each other by the dielectric constant of the dielectric material. So there's two, and this, I know this has gotten confusing, so let me try to clarify it. There's two constants that I've introduced now. Both of them are designed to describe the properties of the dielectric material. One is the permittivity just of the dielectric, okay? And the permittivity, as I've said before, is a measure of how easily the electric field can pass through whatever your dielectric material happens to be. The other one is kappa, the dielectric constant, okay? And that essentially that doesn't talk about the electric field particularly. It talks about how much the capacitance of the capacitor will get changed using this. To be a little more, I shouldn't say truthful maybe, but closer to the real meaning of kappa, remember that the whole reason that the dielectric material reduces the internal fields is because the molecules of the dielectric get polarized in the presence of the capacitor's electric field, the field from the plates. So kappa is a measure of how strongly or not a particular material can polarize. And so the larger the value of kappa, the more strongly the dielectric material gets polarized when it's inside the field. So epsilon, that is to say the permittivity, measures how easily the electric field can penetrate and pass through the dielectric material, whereas kappa tells you how strongly the dielectric material polarizes in the presence of an electric field. So they're related to each other, as you see, but they are discussing different things. Okay, related things, but different. Right. So with all that said, the relationship then, we can replace epsilon with this. So kappa is epsilon over epsilon naught, and so trivially epsilon is kappa times epsilon naught, and so I'll replace that so that so I'll substitute that in. And so the capacitance of the capacitor with the dielectric, still A, still over D. Epsilon now, I'm going to replace it with kappa times epsilon naught. Okay, and then I'm going to rearrange this. Pull the kappa in front, pull the epsilon inside, and you'll notice that this quantity inside parentheses is just the capacitance of vacuum. And so the answer becomes the capacitance of the capacitor with the dielectric is related to the capacitance of the capacitor without the dielectric by simply multiplying by the dielectric constant of the material. And that's pretty darn simple. Okay. And by the way, it follows, I won't bother to show it here, but you can probably pretty easily develop it yourself, that the new electric field is with the dielectric is related to the electric field without the capacitance, again, simply by multiplying by the dielectric constant. Okay. Well, that wasn't so bad.